Okay, welcome to class, everybody. Welcome to a beautiful Wednesday. Summer's coming to an end. I hope you enjoyed your Labor Day. Let's start by talking about our learning objectives for today. We have what I think is the sweetest demo of the whole semester today to see, which is pretty rad. And we're going to use it to explore what variables dictate what phases are present, right? We'll talk about a unary phase diagram as well as a binary phase diagram. We're going to use something called Gibbs phase rule to predict under different temperature, pressure, composition, how many phases are present. We're going to talk about eutectic phase diagrams, including vocab like liquidus and solidus lines. And if we have time, we'll get into solid solubility, okay? Before we get started, I have a quick announcement. IM Flash, that's the joint Intel Micron venture, IM. They make flash memory, solid state memory. They're that giant factory in Lehigh. If you haven't seen it, it's rad. They pay phenomenally well. Internships are coveted there, jobs are coveted there. And one of the main things that they use to recruit, which I think is just awesome, is they hold up here at the University of Utah a tech talk, right? You guys can all apply. It's not meant for graduate students. It's not meant for students who are graduating. It's meant for you guys, right? What you do is you do a 5-minute talk. You don't have to be experts in this. The talk is on the subject, the Internet of Things, cloud computing, automation, automotive. How are semiconductors and 3DX point technology driving innovation in today's fast-paced business sector? That's a horribly long title, but that's what you have to work with. What you have to do is do a little bit of homework, find out what in the world 3DX point technology is, right? Do a little bit of homework and do a quick survey of what's happening in this field, and that's your tech talk. You don't have to feel like, oh, I'm not an expert in semiconductors, or oh, I'm not an expert in memory, or whatever. You can go and give a tech talk. Students from my research group have won it 2 of the last 5 years. So if you want to get an internship, they recruit heavily from the winners of this. They give them internships oftentimes. I think you got to look at it. Your abstract is due in a week on September 12th, and the presentation is on the 19th. I think this is worth your while to at least submit an abstract for this thing, okay? Another quick announcement is there are some keys left in the breezeway, some Subaru keys. If those are you, talk to me and I'll put you in touch with the keys, okay? Okay, so let's get started today. Phase diagrams. This whole chapter is about phase diagrams. Phase diagrams, think of them like a treasure map. A phase diagram tells you where to find the phase of interest, right? Now a map, a treasure map, you've got, right, X marks the spot, and you might have latitude, you might have longitude. In a phase diagram, we're not talking about a physical position, we're talking about the chemical or the thermophysical properties associated with whether a phase exists or not. So things like temperature or pressure, or what if you mix different things together, right? That's what we're talking about when we're describing phase diagrams. So the question I have for you guys, and I want you to turn to a neighbor to discuss, is why on earth do we care about phase diagrams as engineers? Okay, what do we think? Why, as engineers, should we care about finding X on the map, right? Let me ask Becca. That's right, Becca. What do you think? Why do we care about phases?
Because as engineers, we work with pressure and temperature a lot, and it's important to know which phases are in what pressure and temperature.
Yeah. What if, in phases, as you've read in the chapter, if you've done the reading, that could be as simple as liquid, solid, gas, right? What if you have a solid piece of metal, you go too high of temperature, it becomes a liquid. That's probably going to influence the outcome of your device, possibly negatively, right? Maybe positively, okay? Yeah, so let's talk about the phases have different properties. Phases have properties. Right? What else? Anybody else have a thought? Why do we care about phase diagrams? How about in the striped soccer shirt in the back? I don't know your name. Yeah, what's your name first off? Brad. What do you think?
I was kind of thinking along those lines, like,
Okay, to know the limitations, right? Anybody have another thought on why we ought to care about these things? Yeah, what do you think?
If you need a specific structure, because some
Yeah, maybe you want to achieve a specific structure. How about when you process these things? You know, steel, you might order it from a manufacturer, but maybe you're going to do something to it. Maybe you're going to hot roll it or cold roll it. These processing we're going to talk about later this semester, what's that going to do to the phases present or the properties, right? The phase diagram can lend some insight into processing. Let's just give you a quick example, right? Imagine this. You're going to turn to a neighbor. Let's say that you've got two phases. Maybe it's like a ceramic and a metal, right? And the phase diagram tells you that you have 75% by volume of phase A. Let's say that's the metal. And you've got 25% of the ceramic. I want you to, with a neighbor, sketch down all the different ways that those might be arranged, right? Physically, if you looked at it, where are those different phases at? What are the different ways that they could arrange themselves? So turn to a neighbor and give that a shot. Okay, different ways to arrange these things. How might they be arranged? You've got 75%, 25%. How do we put them together? Any thoughts? Anybody? Yeah, what do you think? Spencer?
You could have phase B in solution in phase A.
So completely dissolved. That's an interesting point. So when it's dissolved in the phase, then we only have one phase. That's a really good guess, but in this class, when something's dissolved in another one, we're going to call that a single phase mixture, right? We're talking about when you go beyond the solubility limit, as it's called, which we'll learn about today, and it actually precipitates out what are different ways we can arrange it. That's a good guess otherwise. So we're not talking about A and B as atoms. A and B are phases now, okay? Other thoughts? How can we put them together? In the way back.
side by side.
Okay, maybe like lamellar, right? Let's draw like things like this, side by side maybe. I don't know if this is what you were picturing, but if this is one way of arranging it, okay, let's consider that one for a minute. What other ways could we have? How else could we put them together? Stacked. So this is sort of a stacked. Other ways we could put them together? What if you had like a bulk of, let's see, the 75% A, but you had dispersed amounts of B in it, right? We call these precipitates or dispersions, right? What else? Could we do other things? Yeah.
Could we do like a subset, like smaller circle inside the side of the large circle?
Yeah, you absolutely could. You could have hierarchical structuring, right? So basically you've got like maybe like a ring, but the inside is also A. That's also maybe a possible scenario. That's going to be harder to make, but that's possible. What else could we have? Anything else? Have we exhausted the geometry of putting these things together? What if you had like sort of veins connecting it throughout, and this was all one phase along these veins, but the rest of it was another one, right? Now what I want you to think of is there's other ones we could come up with. But even these four, right? If one phase is a ceramic and one is a metal, how is that going to influence your properties overall of your bulk material, right? This is if you zoomed in on a microscope maybe, but the bulk property, let's just take electrical conductivity for a minute. If the red phase is the metal, and I might have messed this up, but if the red phase is the metal, is this one going to be electrically conductive? Nope, not likely, because these aren't connected. They're not what we call percolated, right? These ones are percolated in certain directions. This guy's percolated, but these aren't, right? Thermal conductivity might be very similar. If your ceramic is a poor conductor of heat, you might expect a similar scenario. What about strength, right? We haven't learned about this yet, but by the end of this semester, you'll be able to predict which one of these you would expect to have more or less strength, right? And lots of other properties depend on not only what phases are present, but how they arrange themselves. And one of the cool things about this chapter is we learn how to achieve some of these different, what we call microstructures. So the first vocab I want you to write down, microstructure. A microstructure is simply what phases are present and where they're located, how they're connected, what's the composition of them, right? How big are they? How small are they? That's the microstructure, okay? So to get started, let me actually pull this up on video because I always forget about each year. Okay, this might work. This is a pretty cool demo, and I will hopefully not burn this place down. I haven't burnt it down yet in 5 years. Okay, what I've got here, those in the way back, there's a piece of iron wire stretched between two posts. And then what I've done is I have what's called a variac. A variac just takes the voltage from the wall, which is 120 volts, at 60 hertz, right? That's the oscillation frequency, because it's an AC signal. It turns it into an AC signal, but with less voltage. It goes all the way down to 0, so I've got it set to 0. And if I cranked it all the way to 100%, it's going to give me 120 volts connected to this iron wire, okay? So the question is, what's going to happen when I start to turn this dial? So turn to a neighbor, what's going to happen? I don't like any of those, but... Okay, what's going to happen? Anybody have a thought? What do you think over here? What might happen? When I start to turn that knob, what's going to happen? You there? I'm going to pass current through it, which will do what? Don't know. Anybody have thoughts? It will pass current through it. In the way back, remind me your name. Jordan, what's going to happen?
The wire will heat up.
The wire's going to heat up. As I pass current through this, we get what's called joule heating. Joule heating, joule is a form of energy. It comes when you pass a current through something that's not a perfect conductor. So it's going to heat up. I agree. It should heat up. What else will happen? Anybody? In the red polo, remind me your name.
Harley.
Harley, what's going to happen? It's going to heat up.
Heat up whatever's hanging in the middle there.
Oh, good question. What's hanging in the middle? We've got a magnet stuck to the iron wire, and then this is just a weight so that it kind of is drooping in the middle. It makes it a little bit easier to see what's going to happen. So that will also heat up a little bit, correct. What else? The magnet is, we have one vote that says the magnet might move up, like up the wire. That's one vote. It's possible. What do you think?
I think the wire's going to lose its magnetism. The magnet will fall off.
The magnet may let go because the wire, what we're going to say, loses its magnetism. We'll talk about that later this semester. That's a good guess. What else? As it heats up, what should happen to this thing? What do we learn about in the very first chapter? Thermal expansion. The vast majority of things, when you heat them up, they get longer. So what should this wire do? If the ends are fixed, what should happen to the wire? Should droop as we heat it up. Okay? Let's start doing this. So, pass current through it. I should really bring glasses for this. I get so nervous doing this every year. Okay, what's happening? What's that? It's not steam. It smells. It's not enamel. It's a good guess. What is it? First off, this is iron wire. Same stuff you could bind fences with, or I bought it from a craft store. I don't know what they're doing with it there. So if you don't put oil on iron, it corrodes. It forms rust, right? Rust forms very, very easily. It doesn't form a passivating layer. So they put oil on it, and that blocks. That's the passivating layer that keeps air from corroding your wire. So when we passed current through it, it got hot enough that it just nuked our oil, okay? So we no longer have oil. What's going to happen if I keep on turning this? It's just going to keep on heating up. So let's do so. We're at 20%. I feel like I'm in Star Trek here, the shields are at 25%. We're at 30. All right, now we're at 30. Okay, what's happening? You see something going on now? It's sagging like crazy. Notice there's red spots. Why are there spots that are red? This is really red right there, and that sort of kink. Why are certain spots red, but over here's not all that red? Yeah, the resistance is not constant throughout our wire. The resistance is not constant. There's spots that are more electrically resistive, and therefore there's more joule heating. And at the kinks, that's one of those spots. And by the end of the semester, you'll be able to explain why a kink resists electricity a little bit more. Okay? So we keep on going. Let's take it up to 35. Start getting sketch. Watch the height, if you will. Watch this height. I'm going to take it up to 40. It's getting quite hot. I can feel it from here. For the YouTubes. All right. We're at 42. Watch the magnet. 45. Oh, gosh. 50. Okay, our magnet's gone. It's probably melting my plastic there. I'm going to take it up to 50. Now, I'm going to kill the power in just a minute. I'll take it to 55. I don't want to trip a breaker. I've done that before. I'm melting my wire sheath over there. Okay, watch what happens in terms of the height when I kill it. I'm going to kill it right. We're at 60. 60. Okay, I'm going to kill it. 1, 2, 3. Watch the height. Up. Down. And then back up again. So explain that physics to me. Like, what on earth is happening? What was that about? It made all the sense in the world when we were heating it up because it looked like it was just continually moving down. If you watched closely, had I done it a little bit faster, it was going down. It actually went up subtly, and then it went down again. And when we killed the power, it did the opposite. It was shrinking, 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 expanding, and then shrinking again. So help me understand what on earth is going on here. What do we think? What's going on here? Let me pick on Courtney. What's going on? There's a phase change. At a certain temperature, there's a phase change. She's exactly right. What we call iron, like the very basic Gen Chem version of phases is like solid, liquid, gas. She said the key thing here. There's a phase change even though this is still a solid piece of iron wire, right? It's still a piece of solid iron wire, but it underwent a phase change. Now, what do we know about the phase change? Since the length changed, what can we say about the two phases? Do we think they have the same volume or no? Probably not. Because at high temperature, we kept on heating this thing up, and it was drooping, but all of a sudden, at the phase transition temperature, it shrunk. That means that iron has a different way of arranging its atoms at high temperature, which is more compact. Right? The number of atoms in this wire hasn't changed, not appreciably. Right? If there's like a billion atoms here, or whatever number there is, that hasn't changed. What has changed is the way that those atoms have come together. And at high temperatures, they choose, because it's thermodynamically favorable, to squish together a little bit. And that causes the whole wire to contract, which made it go up. And then once that transformation was complete, it kept on getting longer. Thermal expansion took over again. Right? So when I talk about phases, we're not just talking about solid, liquid, gas. There can be different phases even though they're all solids, right? So let's dive into this a little bit, right? And we're going to start with our simplest scenario, which is water, right? Let's draw the phase diagram for water. Okay, the phase diagram for water is kind of unique, actually. Life on this planet could not exist if it wasn't for a quirky thing about the phase diagram of water. When we plot pressure versus temperature, and you remember that Gibbs free energy is equal to is equal to H minus Ts, and that's equal to U plus PV minus Ts. So Gibbs free energy, it depends on a lot of things. Pressure, volume, temperature. Last class, or a couple times ago, we learned that it also depends on the number of moles, something we called the chemical potential. We'll talk more about that this chapter. We're just plotting it against temperature and pressure for a minute. Because if we included the other things, we'd have to have like a 3-dimensional figure or a 4-dimensional, and we're not going to do that. That's hard, right? Let's just consider pressure and temperature for a minute. There are what we call phase boundaries. Boundaries, right? They're conditions at which you switch from one phase to another. So water has this kind of funny Y-shaped curve, and I'm exaggerating it. The left part of that Y is not nearly that far leaned backwards. I'm just exaggerating it here. But over here, we're going to have solid, liquid, and we're going to have gas. Okay, solid, liquid, and gas. There is one point on this entire, what we call a unary phase diagram. It's unary because this is all H2O. This isn't H2O plus salt or H2O plus sugar. This is all just one substance, H2O, right? And there's one point on this plot, right there. Let me switch color. Let's call that point A. Point A, solid, liquid, and gas, are all in equilibrium. All three of these phases are in equilibrium at point A, right? We can draw some other points. Let's say that, that this is 1 atmosphere, right? That's where we live, is at that pressure. So we've got this right here. Let's call it B. This one right here, let's call it C. And then let's take one out here, and we'll call it D, right? At these 4 points, let's talk about what phases are present. At A, we said solid, liquid, and gas are all in equilibrium. They're all present. At B, that's when you have your solid and your liquid in equilibrium, right? Solid and liquid in equilibrium. We call that what? Your freezing point, right? Or conversely, your melting point. Whichever, either thing. Depends on which direction you're going. Same thing. What about C? When your liquid and gas are in equilibrium, what do we call that? Your boiling point, or I guess you'd call it your condensation point if you're going the other direction, right? Same thing. So these lines, what they're doing is telling you is where are the boundaries between different phases, okay? Now, the reason that life can exist on this planet is because of this quirky thing right here. This thing right here has a negative slope. It's tilted that way, when the vast majority of other substances are tilted that way. Think about it for a minute. If you take a liquid is a very disorganized arrangement of atoms. A solid is, generally speaking, a more condensed version of atoms, right? And therefore, if you were to increase pressure, you start out with a solid, you would not expect it to turn into a liquid. But that's what happens with water. If you take an ice cube and you were to squeeze on it, and you squeezed it hard enough that you crossed this boundary, it would no longer be thermodynamically stable in the solid form. Your ice cube would turn into water. This is what they thought for a long time was the reason why people could ice skate. It's actually been debunked. They thought that, oh, all the pressure of your body is on this thin little blade. That must mean that as you're skating, you're locally increasing the pressure quite high, and that's melting the surface of the ice. That's been debunked. It's actually a different reason. That's a good guess, but science was wrong. All right? But think about this. This means for ice, when you freeze it, right, when you go from here over to there, solid ice is a larger volume than liquid. If it was the other way around, if you squeezed solid, it wouldn't turn into a liquid. The fact that ice floats is unusual. A solid is less dense, it's more open space than liquid. And this has to do with water forming hydrogen bonds. It forms a, we're going to show the structure later in the class, right? If this wasn't the case, then our oceans would freeze all the way through. They wouldn't have a cap of ice on the surface and fish and stuff alive down below it. It would be the opposite. So this is a big deal that this works like that. Okay? The phase diagram tells us that's how it is. Now, we've said what phases are present at points B, C, A, and D. Now we can introduce something called the Gibbs phase rule. Gibbs phase rule says the following. P plus F equals C plus N. P, as it's written here, is our number of phases present at a given point. F is the number of external variables in this system, right? Or think of that as the degrees of freedom needed to completely define the state of your system. That's a better way to think of it. Meaning, what can I change to fix my system under equilibrium, okay? C is the number of components in my system. This is H2O, but we're calling that one component because we're not varying the ratio of H and O. It's just one fixed composition. When we get to binary phase diagrams, we're going to take two substances, say nickel and copper, and we're going to vary the concentration between there. Right now, our composition, or our component is just one. It's just pure water. And then N is the number of non-compositional variables. In this case, that's pressure and that's temperature. Gibbs phase rule is a useful tool. It holds on these phase diagrams and it tells us the number of things we can change without changing equilibrium. Let's go to point A, right? So this is our first clicker question. If I can find it. So go ahead, get logged in. And this is basically the same drawing I did before, right? A is at the triple point, B and C are on those boundaries, and D is out there somewhere else, right? So the question I have for you is, how many degrees of freedom are there at point A? I'm going to show one more time the Gibbs phase rule. Gibbs phase rule, we're solving for F, our degrees of freedom, and you know that P plus F equals C plus N. P is the number of phases. C is going to be 1 in this whole instance because there's only water we're talking about. And N is going to be pressure and temperature. So C is 1 and N is 2 for these questions. What is F? Let me work through this one together because I'm seeing some shaking heads. So if we're solving for F, F is going to equal C plus N minus P. In this example, since we're only talking about pure water, C is 1, N is 2, and then we're minusing the number of phases. So at the triple point, 1 plus 2 minus P, what do we have? So get your answers in. Okay, answers in. We're going to move to the next one. Okay, people think, hopefully. So, how many degrees of freedom are there at point A? Most people think there's 0. What that's really telling us, if we go back to our phase diagram, it means, remember, degrees of freedom is things I can change without changing equilibrium. If I change temperature, if I move to the left or the right, I change the number of phases present. I leave this equilibrium point. If I change pressure, the same problem. So the degrees of freedom is 0. I can't change anything. It's a point on this line. Okay? Let's do the next one. This next one says, okay, what about at the points B and C? How many degrees of freedom do I have? Okay, get your answers in at points B and C. How many degrees of freedom? Okay, I'm going to close that poll. Answers in. Okay, wrapping it. Okay, people think 1. All right, this is basic algebra. But what does that basic algebra mean, right? You all got that it's 1 for the most part. It means that I can change one thing. I can choose one thing I'm going to change. And if I want to maintain equilibrium, the system is going to pick the other variable. So let's take temperature. If I change temperature, say I'm at C, or even better, let's do pressure, right? If I move from, this is basically the boiling point, like of water. If I boil water in LA, does my pressure go up or down? Los Angeles, think of the air as an ocean of air. If I go to the bottom of the ocean, is the pressure higher? There's a higher pressure, so I'd be going up in terms of pressure if I go to LA. What did that do to my boiling point? It lowered my boiling point. Now, if you cook in Utah, when we read recipes and it says boil the pasta for 10 minutes, maybe the person who did that wrote it in LA where he had to boil it for 10 minutes, but that was at a lower temperature. Here in Utah, the pressure is higher. No, we're backwards. Pressure's lower. Excuse me. I'm an idiot. I'm over here. Sorry. I'm on the wrong line. Completely redo it, right? So here's Salt Lake City. Here's LA at a, LA's up here at a higher pressure. It boils at a higher temperature. Okay. Promise I'm with it. Okay. Here's LA, right? It boils hotter there. it boils colder here because we're at a lower pressure, because we're higher in the ocean of air, right? Therefore, we have to cook things for a little bit longer, right? You ever wondered why they said that at high elevations? Unless you're barbarians and you don't take into account elevation when you cook, right? Just possible that there's a few of you in here. That comes from this diagram, right? Okay, and we'll do the last one. Okay, at point E, E's way out over in the middle of the gas phase. How many degrees of freedom do we have? That's exactly why you do it. Just because it cooks the hell out of it, because it's so much hotter. It's boiling. It takes even longer. Okay, get your answers in. Point E. Basic algebra here. Not even algebra. Arithmetic. We're going to close the poll. Okay. Numbers still coming in. Click those answers. Feel bad closing it. All right, closing it. Okay, people think it should be 2. It is 2. All right. So what does that mean? Out here, in this case, it's point D. This means if I want to have 100% gas, right, vapor, be present, I can change both pressure and temperature a little bit, and I still have one phase present. So Gibbs phase rule is a useful thing. It's going to be more useful when we move to other phases, other diagrams that have more than one component. But for now, it's already instructive. Now, the question for you I have is, how did we get these phase diagrams in the first place, right? So take the water phase diagram. This is what water actually looks like. Remember how I said this was exaggerated, this one? I wasn't kidding. Like, it's mostly just straight up, but there is a slight negative curvature. And then look over here in our solid region. There's a gazillion different ices, right? There's not one crystal structure of ice. There's actually 11. And this is just the crystal structure. This isn't the microstructure. The microstructure takes into account that ice is usually not pure ice. It's ice plus air pockets, right? So those of you who are interested in skiing, and you notice that ski conditions can just really vary, and there can be totally different types of snow. Some of it's fluffy and nice, some of it's crappy and slated, some of it's prone to avalanche, and some isn't. That's not taking into account the crystal structure of ice, because that we're probably not going to vary too much from that. We might be just in like 1 or 2 regions there. But it is changing the amount and the location of the air that's present. And that has to do with how the ice grows. So we'll talk about that a little bit later on. Okay? How do we get this diagram? What do you guys think? How would you do it? Experimentally. How would you experimentally figure out this diagram? Put water in a piston, increase your pressure. Yeah, what else might we do? It's tricky, right? Trying to physically observe it is challenging. Later on in this class, we'll talk about some tools that we have to probe the different phases that are present. But for now, it's experimentally determined. From the experimental data, you can calculate the free energy, and then you can use free energy to create these lines. What do I mean? It goes back to our old friend Gibbs free energy, which we just said G equals U plus PV minus TS. And then if we start taking the derivative, we said that dG dt, basically all of these that don't depend on T, we get rid of. This is equal to the negative entropy. If we take the derivative with respect to pressure, the only thing that varies with pressure is volume, right? It's going to be proportional to the volume. So what's cool is you can actually plot what phases are present as you change temperature or as you change pressure. Let's do so. So let's use our phase diagram, and let's say we're going to plot a couple different scenarios, right? So we're going to plot G versus pressure, G versus pressure, G versus pressure, G versus pressure. But we're going to do so at different temperatures, okay? The temperatures we're going to do them at are as follows. I'm going to move this out of the way. Okay, here's the temperatures we're interested in. Let's call that temperature 1. Let's call right here temperature 2, right at the triple point, right? Then you've got temperature 3. And I'm going to skip the other one, temperature 4. We'll just do 3. We'll just do 3, okay? At temperature 1, so this is at T1, this is at T2, at T3. Let's draw some lines. We'll have this be solid. We will have blue be liquid. And we will have, what, green, purple be gas. Okay? So what I'm going to show you is that, let's pick one of these temperatures. Let's start with T1. As I increase pressure at T1, so I'm going straight up from low pressure all the way to high pressure, what phase is present over that entire pressure range? Solid, right? Solid is going to be present over that entire range at T1, okay? I think I actually meant to, I'm going to change this just slightly because it's a little more instructive. I'm going to move it just over a hair, so it's actually right here. That means T1 starts out as a vapor and it turns into a solid, okay? It goes from a vapor to a solid. So when we plot these things, since we're plotting dg dp, the slope of that line is dg dp, is going to be proportional to the volume. And that's the volume of the phase that we're plotting, right? So when we do this, let's plot our different phases. Let's plot which one has the highest volume, gas, liquid, or solid? Definitely a gas. So it's going to have the highest slope, right? So we're going to draw that like this maybe, right? That's our gas. It has a really high slope, okay? What's our next highest volume? Remember, this is water. What is the higher volume, solid or liquid? Unusually, it's solid. Like, that's not typical, but that's the case. So we've got this, right? And I'm just drawing these arbitrarily right now. And then the last one is our liquid has the smallest volume. So if we move to our blue line, it's got the lowest volume. Now, I've intentionally chosen to draw it in this way such that these things intersect right here. At a certain pressure, we can call this P1. And that would correspond to right there. That's P1. Oops. At P1, if we look at our phase diagram, as I'm going up in pressure, oh, it's gone. End note, doing end note things. That's P1. As we go, it's gone. And that one's gone. I just say how much I love EndNote. It's my favorite Microsoft product. Anyways, right there it transitions. So below that pressure, it's the gas phase that is thermodynamically stable. And above that one, it's not. That's what this is telling us. Look at our diagram here, right? At lower pressures, over here, we have the gas phase is present. And over here, we have the solid phase is present. The reason we know that is because why does anything in this entire universe happen? It lowers energy. If I'm a solid, my energy is here. If I can go down in energy to be a gas, why wouldn't I? I'm definitely going to do that, right? So it becomes a gas. Over this range, solid will be a gas. Over this range, it's going to be a solid. And because we drew the liquid line up higher, it's never going to be a liquid at this temperature. And in this diagram, sure enough, it's never going to be a liquid. It never intersects the green liquid section. Everybody sort of following me so far? Let's do another one. Let's do T2. At T2, we're going to draw it the exact same. We're going to keep the same slopes. We're just going to move them around a little bit. So let's go to our gas. Gas is still going to be there. Solid is going to be there. Liquid is going to be there. Right? So now what do we have? We have, let's call it P2. We have a second pressure now. It's going to be, there's P2. As we go up in pressure, we start out as a liquid, as a vapor. we turn into a liquid, and then we're going to ignore what happens higher up because this is a simple scenario for a minute, so ignore everything above that point. Just ignore that for a minute. For this class, we're going to ignore that because it's complicated. Right? So it basically says, over here, you've got a gas. Over here, you've got a liquid now. So increasing in pressure, it transitioned to a liquid. All we had to do is move where these lines intersect a little bit. And we could do it one more time for T3, right? But it's going to look basically the same, okay? Are there any questions about this? I'm going to skip this, actually. Any questions on doing this? We could do it for temperature, too. Let's do it for temperature. So if we plot G versus T, G versus T, I'm going to move this thing. Oh, not the desired result. Try that one more time. Nope. Also not what I was looking for. One more time. Try that one more time. All right. Maybe. Okay, magic. Okay, if we do G versus T, the slope is no longer proportional to the volume. It's proportional to the negative entropy, right? Negative S. So of these three phases, gas, liquid, solid, what has the most entropy? Gas. So we're going to have a negative slope, and it's going to be a high slope for gas. And then which one, liquid or solid? Liquid is now going to be higher, right? So if we go over here, let's go ahead and draw it. Let's go to our gas phase. Right, that would be gas. There's going to be liquid. And let's draw solid. Okay? Now, what temperature am I referring to here? It's one where at low temperatures, medium temperatures, and high temperatures, we have three different phases present. At low temperatures, it looks like solid, then liquid, and then to high temperatures, we've got gas. So what temperature, or what pressure am I talking about? Where in terms of this diagram do we see it go from solid to liquid to gas? Solid, when you increase temperature, solid, liquid, gas. So we must be above the triple point, right? Or the critical point. So that must be at T above the critical point. Not critical, triple. Let's call it triple. That's the right word. Oh, P. I'm sorry. You're right. Thank you, whoever said that. This is at a pressure above the triple point pressure. Okay? This makes sense? What questions can I answer on this? There's got to be a few. Yeah?
What dg over d, or the change of the energy over change of temperature, you're finding the value negative s, and that's units of
What?
temperature.
It has, remember, entropy's units is joules per mole Kelvin. Okay? But critically, just think of it in terms of disorder for a minute. What has the most disorder? We said that the entropy of gas is greater than the entropy of a liquid, and that's greater than the entropy of a solid. And for volume, we said that the volume of a gas is greater than the volume of a solid, and that's greater than the volume of a liquid. But these last two, that's for H2O. That's not common. It's more common the other way around, that liquid is typically denser than solid. Typically. Other way around. Sorry. Solid is typically denser than liquid. But for water, we have this unusual scenario. So the whole point of me saying this is that if you can figure out expressions for free energy as a function of temperature, pressure, atoms present, you can plot phase diagrams. And maybe then you only have to measure a couple of points to calibrate your curves, but you can generate phase diagrams from thermodynamics, which is really valuable because physically measuring these things can be really tricky, can be really hard to do. That's why we study thermodynamics. That's one of the reasons why we study it, is to give us these maps of what phases exist under different conditions. Okay? Let's keep going. We got 5 more minutes. Okay. Now, this all changes a little bit when we consider multi-component systems. And I'm not going to test you on it, but if you want to see the gory, details of its derivation, at the very bottom, I go through it. I describe what happens, right? How does your free energy, your change in energy change when now you have chi? Chi represents the fraction of 2 different components. So if you want to see this, it's here. I won't be testing you on it. It's at the bottom of the notes, okay? Instead, I'll just show you the key things you need to know. Where are we at? Okay, right here. To start with talking about multiple phases, or multiple components, let's consider the simplest phase diagram that has 2 components, right? That's what we call an isomorphous binary alloy. What does morph kind of refer to? Like Mighty Morphin Power Rangers? What's the morph? Change, right? What about amorphous? Something that doesn't have a structure, amorphous. So morph has to do with structure. So when we say isomorphous, iso is the same structure. So this would be a mixture of 2 things which have the same, let's call it crystal structure. We haven't gotten to crystal structure yet in this class, so don't worry about it. It's just ways of arranging atoms. For example, students in this block here are arranged in kind of a rectangle. We could say that they have a rectangular crystal structure. We're going to learn later this semester more accurate terms for it than just rectangular. It's more complicated than that. But think of it like that. Over here, maybe they're like triangular. You got triangular and you've got rectangular, right? If you've got 2 different metals and they both have rectangular ways of arranging their atoms, we'd say that this is isomorphous, okay? That means that as you change out atoms all the way across the series, you can have what's called complete solid solution. What that really means is that if, let's say you start out with pure copper and you've got pure nickel, if I start to add nickel atoms to copper, since they're so similar in many different ways, it'll just dissolve. It just basically, you pull out 1 copper, you put in 1 nickel, and the structure doesn't have to change crystal structure. Maybe it changes its size a little bit, right? Let's say I replaced these chairs with like big sofas, right? Maybe the whole separation distance between these rows has to get a little bit bigger, but it might be able to keep its structure, right? If it's way bigger, then it's going to have to change its structure to accommodate the different size. But if these things are similar to one another, it's not going to have to do that, right? So the last thing I'll cover is let's talk about water and sugar and ask whether it fits this description, right? So I'm going to plot down here the weight percent sugar, and I'm going to plot here temperature, right? When you put sugar in water, what happens? Sugar in water, right? What happens? It's going to dissolve and form what we call syrup, right? So let's say over here, let's call this syrup, right? If you keep on adding sugar to it, like my kid does when he makes Kool-Aid, he crosses a critical threshold, right? Over here, where now we no longer have syrup, what do we have? We have syrup plus sugar, right? It like sinks to the bottom. He thinks that's just awesome, right? But he has discovered, without even realizing it, what we call a maximum solid, not a solid, liquid solubility, because this is a liquid in a solid, right? So this would be a liquid solubility. But that's the solubility limit, right? It means we can only add so much sugar, and then it's going to crash out, it's going to precipitate out. And he's learned that in his hot cocoa, which he heats up, he can get away with putting a whole lot more sugar in there without it crashing out. Because this line, that phase boundary, has a positive slope, okay? So this is the first time where we're now varying the ratio of water to sugar on this x-axis, but that could just as easily be different types of atoms. Pure magnesium and pure lead, for example. What does it look like is where we'll pick up next class.